All right, so let's get started where those videos from the previous summer in my YouTube playlist. We'll start off where I asked you to get to, which was to section 15.4, and now we're going to talk about chemical shift. So if you watched the last video, which was just an introduction to the first four sections of the chapter, now we're going to get into chemical shift in detail. It says here that in many NMR solvents, we add 1% of this compound called TMS. And TMS stands for tetramethylsilane. So we have a silicon here, so it's a silane, and then we have 1, 2, 3, 4 methyl groups. What I'm saying is that anytime you buy a solvent that you use for an NMR experiment, the supplier will always add about 1% of this compound into the solvent. And if you're wondering, well, why do they put this compound, tetramethylsilane, in all of these NMR solvents? Well, the reason why is because the shift for a proton in an NMR spectrum is always calculated in comparison to tetramethylsilane. So that means that tetramethylsilane is the standard for all scientists around the world. If anybody runs an NMR spectrum and they report a chemical shift, it's always reported 100% of the time in reference to tetramethylsilane. And so when we measure the chemical shift in the variable or the letter that we use to represent chemical shift is the Greek symbol delta. So chemical shift is equal to the observed shift from TMS, from tetramethylsilane, measured in hertz, the frequency of the absorbance, divided by the operating frequency of the instrument in hertz. Okay, so let's say you are running a proton NMR spectrum on benzene in a 300 megahertz instrument. So if we draw the structure of benzene, there are 6 protons in benzene, and we see that all 6 of these protons are chemically equivalent. They're all homotopic, they're all identical, there are multiple planes of symmetry in the molecule. So we have one type of proton in this molecule. And when you look at the absorbance, the absorption frequency of these protons in a 300 megahertz instrument, we see that their absorption frequency is 2,181 hertz. So what we do is we divide that by the operating frequency of the spectrometer, which is 300 megahertz, or we have 300 times 10 to the power of 6 hertz. So when we do that, the units of hertz cancel out, and we get a unitless number, which is 7.27 times 10 to the negative 6. Now you might be asking, well, hold on, Mr. Dion, I thought that you said in your videos that, different research institutions or even, chemistry departments will have more than one NMR spectrometer. What if you have, what if UCCS, let's say, has a 300 megahertz spectrometer, and what if, Harvard has an 800 megahertz spectrometer, and then what if CU Boulder has a 60 megahertz spectrometer? Well, that would mean that the observed shift from TMS is going to be different in all those spectrometers, and you would be 100% correct in saying that. However, since we always divide by the operating frequency of the instrument in hertz, we always end up with the same chemical shift for the same protons, no matter the spectrometer we run it on. Let me show you the math of how it works out if we were to run an NMR spectrum on benzene in a 60 megahertz instrument. Well, now the chemical shift is not going to be, 2,100 and something hertz. It's only 436 hertz, but now we divide it by 60 megahertz, or 60 times 10 to the power of 6 hertz. The hertz units cancel out. So this cancels and this cancels, and we end up with the exact same number that we saw on the previous slide, 7.27 times 10 to the negative 6. So the whole TMS thing and the whole dividing by the operating frequency of the spectrometer is a beautiful thing, because scientists anywhere in the world, when they run a proton NMR, they can always communicate with each other. They can say, well, I ran the proton NMR on this compound, and the chemical shift that I saw for this proton was, 7.27 times 10 to the negative 6. And we're going to talk about this more in a second. But anybody else on the planet Earth would end up with the same answer, again, regardless of the spectrometer that they're using. So we saw how the hertz cancel out. Hertz and hertz cancel out. And so the chemical shift is a dimensionless number, okay? But instead of reporting every chemical shift as being times 10 to the negative 6, that gets a little irritating. And so what we do is we get rid of the 10 to the negative 6, and we just say, oh, let's just cross it out. We say ppm. So we just use ppm, or parts per million, right? Because 10 to the power of 6 is a million, so we say parts in a million. All right, and there you go. So most of the proton NMR signals that we would see in this class, it says here on this slide 0 to 10 parts per million. I'm going to actually change that a little bit. I'm going to cross this out. So just bear with me, and I'm going to block that out. And let's put in 0 to 12. They actually lie, I'd say, from 0 to 12 parts per million. That's where we're going to see chemical shifts in chemistry 3101. There is some old vernacular that's used in NMR spectroscopy. I'm going to try to avoid it because I'm not a big fan of it, because it's, it's modern times. However, there are some terms in NMR spectroscopy that have stuck around. One of them are the terms, or two of them, I should say, are the terms downfield and upfield. If you have chemical shifts that are further to the left in your NMR spectrum, we say they are more downfield than the signals that are on the right side. Now, if you're wondering, what do you mean by down, or where does downfield and upfield come from? Well, it's a historical term that comes from what was the old magnetic resonance spectrometers, which were called continuous wave spectrometers. Just to give you an idea, I'm 45 years old, and I've only ever seen one in my life. Okay, it was when I was doing my undergraduate degree. They had an old one in the department, and I don't even know if I ever saw it used. I saw the actual spectrometer, but what they did in the first spectrometers is that they held the they held the frequency constant. So they had a constant frequency of electromagnetic radiation, and then they varied the magnetic field strength. And now we do it the opposite, right? We maintain the magnetic field strength constant, and we vary the frequency of electromagnetic radiation. And so the protons that came into resonance at a low magnetic field, those are called the downfield, and then here we call those the upfield. Again, I'm really rambling on here, but they're historical terms. I'll try not to use them a lot. Instead of saying downfield, I'll just say higher chemical shift probably, but it might slip out of my mouth from time to time. Okay, anyhow, so that's what a continuous wave spectrometer is, but don't really worry about it. I mean, usually what I would say, what Mr. Dion, your instructor, is going to say would be higher energy or higher frequency. I would say that too, so we can put that in here. Higher frequency, chemical shifts, and then we can say here lower energy or lower frequency. Lower frequency chemical shift, right? Because we know that E is equal to H, right? E is equal to Planck's constant times frequency. So we see that energy and frequency are directly proportional. So high frequency is going to be equal to high energy. Low energy will be low frequency. All right. So really nothing, major there. Let's see here. It says here that shielded protons have a smaller magnetic force acting on them, so they have smaller energy gaps. And that makes sense, right? If we have a proton that is surrounded by a lot of electron density, which causes a magnetic field that's going to go against the externally applied magnetic field, that means there's going to be a small gap between the alpha and the beta spin states. And that means it's going to cost less energy to cause them to go into resonance. And so if we have shielded protons, they're going to absorb upfield or at lower energy or lower frequency. Whereas if we have de-shielded protons, they're going to absorb at a higher frequency, a higher energy, or we could say they are shifted downfield. Any one of those ways of describing it is perfectly reasonable. So if you're wondering, what affects the chemical shift? Well, first let's start off with a baseline. And the baseline is if we have an alkane, so any kind of alkane, we did a whole chapter on alkanes, right? It was chapter 4. We spent a whole, couple of lectures just talking about alkanes. Any kind of alkane is generally going to have all of its protons, having frequent or having, having chemical shifts of somewhere between 1 and 2 parts per million. Okay. However, they can be shifted downfield. What would cause the protons to be shifted downfield? What would cause them to absorb a higher frequency or higher energy electromagnetic radiation? Well, it's going to be caused by deshielding. So what's a way that we can deshield the protons? What's a way that we can remove electron density from surrounding those protons? Well, if we attach an electronegative element. And hopefully you remember from your general chemistry days that if you look at the halogens, they go fluorine, chlorine, bromine, and iodine. And the most electronegative of all of these is fluorine. In fact, it's the most electronegative element in the periodic table. And the least electronegative of all of these would be the iodine. So what we see is if you add an iodine, yes, it is electron withdrawing. And so since it pulls electron density away from these protons, they're going to have a higher chemical shift than they would in a methane molecule, which has a chemical shift of 1 part per million. So you see that the deshielding effect causes a higher frequency of electromagnetic radiation to be absorbed, or a higher chemical shift. Then if we put a bromine on there, that's got an even stronger dipole, and so it causes a greater deshielding effect. Then you go to a chlorine, it's even greater. And then if you go to a fluorine, well, it's the greatest of all of these. And so it has a really pronounced deshielding effect. So the idea is the more electron withdrawing substituent that we have in these molecules, that means the more deshielding we have, and therefore we're going to have a higher chemical shift. Not only is it affected by the identity of the electron withdrawing group, whether it's an iodine to a bromine to a chlorine to a fluorine, but it's also an additive effect. We can see that if we have just one chlorine, we saw that the chemical shift was around 3.1 parts per million for chloromethane. But if we have dichloromethane, then it's going to be even more pronounced, because now you've got two dipoles pulling on it, which causes more deshielding. And you can see that if you go to chloroform, which is CHCl3, you have 1, 2, 3 electron withdrawing groups just yanking electron density away like crazy. And so that causes an even higher chemical shift. Now you might be saying, well, hold on, Mr. Dion, every single one of these halogens is attached to the carbon that has the protons on it. What happens if you have a halogen but it's further away? That would be a great question. And what happens is, if you have protons on the alpha carbon, meaning the carbon that is directly attached to the electron withdrawing group, here's our electron withdrawing atom, here's the alpha carbon. Those protons are going to feel the electron withdrawing effect of the electron withdrawing group. Same with the beta protons. They don't feel it nearly as much. You can see their chemical shift isn't as high. However, they do experience some deshielding. But once you get to gamma, it has no effect. So no effect. So what I'm saying is that this dipole isn't affecting these three protons at all. It only affects the alpha and the beta protons. All right, so chemical shift. What did we see on this slide? That the more electron withdrawing group you have, the more deshielded the protons are, and therefore they will have a higher chemical shift. If you add more and more electron withdrawing groups, that exacerbates the effect. And we see that that effect is only manifested in alpha and beta protons. Once you get to gamma protons, the effect drops off, and we don't really see any change in the chemical shift of the protons. Now, in order to predict chemical shifts, and this is something that can be done with accuracy in a lot of cases, what we're going to do is we're going to start with a standard chemical shift for the type of proton, and then we're going to adjust it depending on its proximity to certain functional groups. So these are some baselines that you need to know. A methyl, a methylene, and a methine. You must memorize these values. Memorize. You need to know that the baseline for a methyl is 0.9 parts per million. The baseline for a methylene, which is a CH2, is 1.2. And the baseline for a methine, which is a CH, is 1.7. I repeat, you have to memorize these values. These values are not on the table that you're going to bring in with you to your quizzes, and you're not going to have any tables on the final exam. So these are numbers that have to be memorized, and we're going to try some practice problems today where we're going to employ these values. So methyl has the lowest, 0.9, methylene is around 1.2, and methine is around 1.7. All right, So how is the proximity to functional groups, how is that going to affect the chemical shifts of protons? Well, let's take a look. The first thing is, and again, this is another table you're going to want to memorize. So we'll put here table 15.1, memorize, and it's not very long. I'll show you how to use this table. The first thing is if you have alpha protons that are next to the oxygen of an alcohol or an ether, what you're going to do is that oxygen, remember oxygen is the second most electron withdrawing group or element in the periodic table, or I should say the second most electronegative. So it's going to pull electron density towards itself, which is going to deshield these two protons, for example. And so what it's going to do is it's going to cause them to be deshielded by 2.5 parts per million. So let's say you had a methylene, right? This is a CH2 here. The baseline that we saw on the last slide for a CH2, a methylene, was 1.2. If it's alpha to those protons, you add, alpha to the oxygen of the alcohol or ether, you add 2.5. Plus 1.2 plus 2.5 gives you 3.7 parts per million. And if you look at the actual chemical shift of those protons in ethanol, which is this molecule here, this is ethanol, they are actually 3.7. So you can see the prediction is pretty dang good. Now, if your protons are next to the oxygen of an ester, and I mean the sp3 hybridized oxygen of an ester, so, and that's the only place they could be. But anyhow, then you increase the chemical shift by 3 parts per million. So let's say we have this molecule. This is called ethyl acetate. We learned ester nomenclature in organic chemistry too, so don't worry about that right now. But this effect is even more pronounced. Why is it more pronounced? It's because there's a resonance structure that you could draw here where you show a positive charge on this oxygen. So it's pulling electron density away like crazy, and thus you increase the chemical shift by 3 parts per million. So for a methylene, you would take 1.2 plus 3, which gives you 4.2. And if you look at the actual chemical shift of these two protons, it's actually 4.1. So that's pretty accurate. Okay, very accurate. Now, if you remember a couple of slides ago, what I told you was the alpha protons experience an effect, and the beta protons also experience a slight effect. How slight is it? Well, let's go back here, and you can see in the fine print here, well, it's not that fine. On the bottom, it says the beta protons experience about 1/5 of the effect. All right, 1/5 of the effect. So let's say we wanted to determine the chemical shift of these 3 protons here. So there's 1, 2, 3 protons on this methyl. Let me just draw a circle around one of them. The baseline of a methyl, CH3, was 0.9 parts per million. So let's scribble that down. So let's put down here 0.9 parts per million. And then it says we add 1/5 of the effect. So what's 1/5 of 2.5? It's 0.5. So 0.9 plus 0.5 gives us 1.4 parts per million. And so that is the predicted chemical shift for these 3 protons in this molecule. We could try the same thing for these 3 protons down here. Let's pencil them in. 1, 2, 3. The baseline for a methyl proton, a CH3 proton, was 0.9 parts per million. Now we're going to add 1/5 of 3. 1/5 of 3 is 0.6. So we end up with 1.5 parts per million as a predicted chemical shift for those 3 protons. And that's how we predict some chemical shifts. Now there's one more part to table 15.1. It's right here. It's if your protons are alpha to a carbonyl from a ketone, aldehyde, ester, amide, whatever, what we do in that case is we add 1. So the effect isn't as strong as the other 2 that we saw in this table. So let's say you had these 2 protons right here. The baseline of a methylene is 1.2. We add 1, we get 2.2, and you can see the actual chemical shift is 2.4. So this is a very good predictor. If we wanted to determine, or estimate, I should say, predict, the chemical shift for these 3 protons, 1, 2, 3, like that. So we can put a circle around that. The baseline is 0.9 parts per million. And then we add 1/5 of 1. Who can tell me what's 1/5 of 1? It's not a trick question. I just need a sip of coffee. How many parts per million would I add? 1/5 of 1. Exactly. I'd add 0.2. So 0.2 parts per million. And that gives me a predicted chemical shift of 1.1 parts per million. I repeat, table 15.1. So this slide and this slide, you have to memorize these values. The 2.5 and when to apply it, the 3, when to apply it, and the 1, when to apply it. You also have to memorize the baseline for the methyl, the methylene, and the methyne. Those things are not going to be given to you on a quiz. They must be stored in your brain in order to apply them. Again, we're going to take a look at a practice problem today that covers that in detail so you get some practice on it. And there's also a lot of really cool practice problems in the book that go over this in detail. The next section, which deals with still the chemical shift, but what are called anisotropic effects, and we talk about this term here, diamagnetic anisotropy, is one of my favorite parts of the entire chapter. Diamagnetic anisotropy is such a cool thing, and basically, and it's got this really, complex looking term, diamagnetic anisotropy. Like, what could that mean? All it means is this: different regions of space are characterized by different magnetic field strengths for some molecules. That's really all it means. Okay, nothing more than that. So check this out. And this is a very specific case, but it's really the only one that's discussed in detail in our textbook. It's an aromatic ring. So let's say you have an aromatic ring, and that's what they're trying to show here in this picture. They're not showing the double bonds, right? They're not showing them. They're just showing 2 protons, even though there's 6. Okay, so what you're seeing here is this. Okay, and again, they're just leaving out these protons, which are all chemical equivalent. They're just leaving them out for simplicity's sake. So what they're saying is this. Very cool. So see if you can follow along with me. If you take benzene, okay, you put it in an NMR spectrometer, you subject it to the externally applied magnetic field. Well, what that does is it causes all the pi electrons, okay, in that ring to start going around, and they create a magnetic field. Okay, now check this out. So I'm sure that you've seen a benzene drawn like this if you've ever perused on the internet, where they draw a circle like that, okay, to show that the electrons are delocalized throughout the ring. And I think we discussed that when we talked about resonance. So check this out. Here are those electrons, right? They're going around and around and around, okay? And what that does is it creates a magnetic field. Here are the magnetic field lines. That's all these little dashed lines going up and down and up like that. But look at what happens. You see how in the middle of the molecule that the magnetic field caused by the circulating pi electrons is going down like this? So remember, if the magnetic field is going against the externally applied magnetic field, that causes de-shielding, right? We have de-shielding here. So, or sorry, shielding, I should have said. So we have shielding going on here. Whereas on the outside of the ring, where the protons actually are, I'll use my green pen, the lines are going along with the externally applied magnetic field, right? They're going in the same direction. And what that causes is de-shielding. Put it another way, just follow along with me very carefully. What it means is inside the ring, there's no protons inside the ring. So we'll get to that in a second. But inside the ring, it's shielded, whereas outside of the ring is de-shielded. So you got the same molecule, and you've got 2 different environments, really, inside or overall for the same molecule. So you've got a de-shielded region, which is outside the ring, and you've got a shielded region, which is inside. So what happens with a molecule like benzene, since all those protons are outside of the ring, they're even more de-shielded than you would expect, right? If you look at carbon-hydrogen bonds for an sp2 hybridized carbon, and remember that every single carbon in benzene is sp2 hybridized, what we see, and I'll show you this in a second, is that they actually have a higher chemical shift than you would expect, and it's based off of diamagnetic anisotropy, which is pretty cool when you think about it. So nothing more than that. those regions outside the ring have an increased magnetic field, and therefore, those protons have a higher than expected chemical shift. Nothing more than that. So what is the chemical shift? Well, the protons in an aromatic ring usually show up around 7 parts per million. In fact, this is a spectrum that we looked at earlier today. And so if this is 7 parts per million here, you can see that we have this group of protons here. Those are the aromatic protons, the ones that are highlighted in red. The other ones, and these two here are these ones, and then these three here are these ones. And I'm going to explain that in more detail in a second, but you can see that those are not directly attached to the ring. So they are, especially the blue ones are de-shielded, but to a small extent. And I'll get into that in more detail. The idea is, and let's see if we can put this all together, is that since the red protons, meaning all 5 of these, since these experience such a large magnetic field caused by diamagnetic anisotropy, that means there's a huge energy gap, or a bigger energy gap, between their alpha and beta spin states. And thus, in order to get the protons to come into resonance, we have to apply a high energy frequency. And so that's why these are shifted so far downfield. Give me a thumbs up if you're with me on the concept of that. Even if you're with me 60% of the way and you're like, you know what, Mr. Gann, I'm going to have to go back and read it. But yeah, I think I follow you on the idea of it. Yeah. Proton theory, the rationale behind proton NMR is definitely something that all students have to go back and we'll have to read it. Sometimes students have to read the section multiple times because, let's face it, it's very different than synthesis, right? Well, we're really doing a complete 180 and trying something very different in chapter 15. So this is essentially the table that I give you for your quizzes. It's not exactly this, but it's close to this. Okay, it's basically like a paraphrasing this table, because I don't give you these structures. I just kind of give you this part, the methyl and the chemical shift of that. All right, and what you're going to find is that the more that you practice, the less you're going to have to refer to that handout, because you're going to start to just know these values. You'll become so accustomed to using them over and over and over. Let's go through all of them kind of quickly, because there's no way you could memorize them all in just 2 minutes of looking at it. I'd say that's humanly impossible. Maybe somebody can, but I couldn't. We've already covered these 3. The methyl, the methylene, and methine. We already covered what their baselines are. And notice that it doesn't say exactly 0.9. It says around 0.9, around 1.2, around 1.7. These are not hard and fast values. These are good approximations. Then if we have an allylic proton, so remember that if we have a double bond, that the protons that are attached, oops, where's my blue pen? Here we go. Remember that these protons are called vinylic protons. You see one over here. We'll get over to those in a second. But an allylic proton will have a chemical shift of around 2 parts per million. If you have a terminal alkyne, so this is, remember, this is an sp hybridized carbon, hydrogen bond, that hydrogen will have a chemical shift of around 2.5 parts per million. Same thing with an aromatic methyl. So an aromatic methyl is around 2.5-ish. Next, we come over to the alkyl halide. So, and we saw that today, whether you had, an iodine, a bromine, a chlorine, a fluorine, it was roughly in the region of 2 to 4 parts per million. Alcohols are kind of interesting. I'll talk about those in detail and why they have such a wide range of chemical shift values, which are very difficult to predict sometimes. Next, we have vinylic protons, which also have a pretty high chemical shift. And we don't go into the entire rationale as to why that is in this class. But if you wanted to do some research on it, you could find out why these things have such high chemical shifts. Then aryl, we saw, the book said around 7 parts per million, but here it's saying, anywhere between 6.5 and 8. Aldehydes are kind of a dead giveaway. They're at 10. And I told you that we go all the way up to 12 parts per million. And the proton the acidic proton in a carboxylic acid is at around 12 parts per million. So again, I'm not asking you to memorize this table today because I'm going to give you the handout, which has, I think, all of these chemical shifts on it. But you want to become familiar with it. And, you know, again, I sound like an old person, but the more practice that you do, the more you're going to become accustomed to these, and just the better you'll get at it, to the point where it will become second nature for you by the time, you know, you get into organic chemistry too. So let's try a problem that applies. We're going to apply this table, table 15.2, and then we're going to also apply table 15.1. So a little bit of everything here. And I might have to rifle back and forth between the two tables here to do a little bit of explanation. But let's start with the aldehyde proton. Sorry, my Apple Pencil is really acting up here. Okay, let's start with the aldehyde proton here. Who could tell me what the chemical shift of the aldehyde proton is, approximately, based on that table that we just looked at? Anybody? Don't be afraid to unmute your mic and interrupt me or holler it at me. You won't offend me. Anybody get the... Yeah, thanks, Zoe. Absolutely. It's 10 parts per million. Let's scribble that in, 10 ppm. All right. There we go. So we got that one. Thanks, Nicole. Thanks, Kiana. Those are all perfect. You're all 100% correct. What about this one here? This is an alkynyl, you know, carbon-hydrogen bond, because this carbon is sp hybridized. Could anybody tell me what the chemical shift of the proton in blue would be according to that table that we just looked at? You could go back here. Yeah, thanks, Kiana. Absolutely. So if you're wondering, you know, how did Kiana know that? All she did was she went here and she said, if you have an sp hybridized carbon-hydrogen bond, the chemical shift will be around 2.5. I say she's 100% correct. So let's scribble it in here. So this is around 2.5. I'm just going to write 2.5. You can put the little tilde like that, which means approximately 2.5 parts per million. Either one is totally fine. I'm just going to remove that. What about, let's pick these protons here. Now this is where it gets a little more interesting. Let me use my black pen for these two here. So I'm going to help you out with these ones a little bit, because these ones are allylic protons, right? If you have a double bond with a carbon attached to it, right? Remember that this is a vinylic position. This is vinylic. This is vinylic. Whereas these protons, 1, 2, 3, those are allylic. So since we have a double bond, this would be a vinylic proton, this one in blue. This would be a vinylic proton, this one in red. But the two that I have in black, those are allylic protons. And we saw that the baseline for an allylic proton, if we go back here, let's go back, was around 2. Okay, now hold the phone. We can't just say that it's 2 because they're allylic. So let's scribble that down here. Allylic. So we'll put 2 parts per million, but they're alpha to a carbonyl, right? This is an alpha carbon. They're next to the carbonyl. So let's go back a couple more tables. Where was I? Before diamagnetic anisotropy. And we said if the protons are alpha to a carbonyl, then you add 1 part per million because of the de-shielding effect of the carbonyl. So let's go back here. So now our allylic protons have a chemical shift of 2 parts per million, but we're going to add 1 to it, and we end up with 3 parts per million. Give me a thumbs up if you just follow me on the rationale for that. Like Mr. Dion, I see where you got that number. Okay, because it takes some practice. It totally takes practice. Nobody could just identify that immediately. You have to work at it a little bit. The vinylic proton, though, let's do the one in blue. So for the vinylic proton, we said the chemical shift was around 4.5 to 6.5. So let's go back here. Where is it? Vinylic was around 4.5 to 6.5. Now, depending on how fussy you want to be, you know, it says it in the table. It's 4.5 to 6.5 parts per million. But these are also beta to the carbonyl. So you would add 1/5 of 1 part per million. So that's 0.2. And so instead of saying 4.5 to 6.5, you could pencil in 4.7 to 6.7. I didn't look at the solutions manual. I'm not sure what it says. It might say 4.5 to 6.5. Why would that still be okay? Because it's such a big range, it's close enough anyway that you're going to have a very good idea of where the protons would absorb. If we go to these vinylic protons, or this vinylic proton here rather, ooh, son of a gun, where's my red pen? Let me see here. There we go, my red pen. This one here is vinylic. It's not alpha or beta to a carbonyl. So we could just put here 4.5 to 6.5 parts per million. Here, I'm going to use my green pen just for a second. These two are, those are allylic protons. So we have allylic protons here. They're not alpha or beta to anything. So I'm just going to write an arrow here and put around 2 parts per million. Then we have these two protons here. This is just a methylene. It's not alpha or beta to anything. And so we said the baseline for a methylene was around 1.2 parts per million-ish. So somewhere in that neighborhood. So let's just write here around. Or right here around. Well, I can't pencil it in right now because I seem to be experiencing issues with my Apple Pencil. Just bear with me here. I should have around 1.2. Let me try again. Okay. Okay, so anyhow, I should pencil in around 1.2 parts per million, but I can't at the moment because my Apple Pencil seems to be misbehaving. So why don't we take a short break and then we'll come back and we'll try the one that's below it.